Cambridge AS Computer Science, Chapter 1, Information Representation, Part 2. Okay, we are here after studying the two's complement. The two's complement is about representing positive and negative numbers. Okay, the two's complement format, for example, let us start from here. I think we stopped here. The range of integer values that is possible to represent in two's complement integer using a single byte, 8 bits. Okay, so the exam may ask you, you are given 8 bits two's complement. You are given 8 bits two's complement. Then the weights would be 1, 2, 4, 8, 16, 32, 64, negative 128. And this is when they are 2 bits. The range of integer values. Okay, what is the lowest value? The lowest value is the most negative value. So if you like, for example, you say, I'm gonna fill this. I would like the lowest value. I put 1 here because this is the only negative component, and I put nothing here. I put them all zeros. 64 because it is positive. You don't like anything positive to be added to this. Otherwise, it will not be the lowest. So you put 1 here, and all these negative, all these zeros, you multiply and add, and then you get negative 128. So the lowest value in 8 bits two's complement is negative 108. The highest value in 8-bit two's complement, you cannot put 1 here. You have to put it 0, otherwise the value will be negative. And you fill them all here. You fill them all here with 1s. So you get the most out of them. So it's going to be 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, that is equal to 127. You may just count them yourself. You may just add them yourself. Or you may say, this is 64, twice of it is 128, minus 1 is 127. It is as if you are storing data in only 7 bits, because it's going to be 2 to the power of 7. Okay, so this is the lowest value that can be stored in 8 bits two's complement. This is the highest value that can be stored in 8 bits two's complement. Okay, let us now extend the number of bits to become 12. Definitely, you will have a larger range. Okay, the range of integer values that is possible to be represented in two's complement integer using 12 bits. Okay, let's make this 8 bits. Okay, here 8 bits. A single byte is okay, 8 bits. Okay, here it's not a single byte anymore. It is 12 bits. Using 12 bits. Okay, so your weights is going to be 1, 2, 4, 8, 16, 32, 64, 1, 2, 8, 2, 5, 6, 512,024. And the 1 on the far left will be negative 2048. Okay, so if you'd like the lowest value, you fill all positive components with zeros, and you fill the only negative component with 1, and it's going to be negative 2048. If you want the opposite, you want the highest value, you do the opposite. You fill all these with 1s, and the negative component with 0. So it's going to be 1024 plus 512 plus 256 plus 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. And this is going to be equal to 1047. Just try them yourself. Try them yourself. Okay? Or you may think that this is 2 to the power of, this is 1, this to the power of 0, power to power 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it is 2 to the power of 10. ماشي? 2 to the power of, so it is 2 to the power of, okay, you may think that twice of this minus 1, twice of this minus 1. Okay? Okay, that is 2 to the power of 11. It is 2 to the power of 11 because this is 2 to the power of 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It is the number of bits is 11. You have 11 bits. So it is 2 to the power of 11 minus 1. And then if you already memorized the 11, the 2 to the power of scale. Okay, anyhow, that was an example of finding the lowest value. That was an example of finding the highest value. I hope this is clear. Okay, let us move to another point. And definitely, I'm training you using exam questions. And I saw this question just 2023, and I have it here in my notes. So let us go through this exercise. It is really modern and not so easy. Convert the denary numbers 1, 2, 7 and 12 into 8 bits binary. Okay? And then perform the subtraction of 12 minus 129. And you have to do this subtraction in binary, and you have to show your workings. I have a little problem. The result is going to be negative because it is 12 minus 127. If you do them in denary, if you do them in binary, definitely, the answer is going to be negative. And you cannot do this in denary and then convert. You cannot. You will not get the mark. So please start doing this yourself. Do this yourself. Please convert the 12 into 8 bits binary. Please, right now. I will leave you for a moment. My plan will be like that. I will convert 12 into 8 bits binary and convert the 127 into 8 bits binary, and then get the 2's complement of the 127. We did all that before. We did that all the lesson, or the previous lesson. However, I just wonder if you practiced enough or not. It is not enough to listen to me. You have to practice a lot using your own paper and pencil. Okay, so I have 12 minus 127. Please get me the 12. This is the 12 in binary. Do it yourself and check with me. This is the 127 in binary. Do it yourself and check with me. And then my plan will be as follows. You may subtract this from that, but I guess it's going to be difficult because there are going to be lots of borrow. So my plan will be like this. You have to subtract 127. I recommend that you get the negative of 127. That is the 2's complement of 127. Remember the FAS method? Remember the FAS method? Okay, starting from the right. If you find zeros, copy the way they are until you get the first one and copy it the way it is. And then start flipping every 0 to 1 and every 1 to 0. Please work independent of me. Convert the 127 into binary. It's going to be like this. Convert the 12 into binary. It's going to be like this. And then get to calculate 12 minus 127 in binary. We turn 127 into negative 127. So we turn, okay, we turn this into a 2's complement. That is that. Yalla ya shabab, please do the conversion yourself. I'm trying to hide my answers. Do the conversion yourself. Okay? Do the conversion and check it with me. This is negative. I will color. This is negative 127 using 2's complement. This is negative 127 using 2's complement. And guess what? Then we may add the 12 plus negative 127. It is that we add this value to that value. Okay? Okay, we add this value to that value. The answer should be this. I will leave you. I will leave you for a moment. When you do this, see, here is the addition, but I don't want to show it to you. Please be responsible and do it yourself. Okay, so using borrowing, okay, with subtraction is little bit difficult. I would love to do it like this. I would love working using to actually this is a screenshot of the mark scheme. This is a screenshot of what I found in the mark scheme. Okay, so okay, let's go to another question. Okay, let us look here. Maybe this is another question. You need to subtract two numbers. You need to subtract two numbers. 1 0 1 1 0 1 1 1 minus 0 1 1 1 0 1 0 1. Okay, this is another question. Let us go through it. You may need to subtract these two numbers. 1 0 1 1 0 0 1 0 1 1 minus 0 1 1 1 0 1 0 1. This is a different, I'm sorry, this is a different question. Okay, so subtract Okay, so it is another subtraction. So you can do it in either way. You can do it in either way. Either using borrowing. So 1 minus 1 is 0. 1 minus 0 is 1. 0 minus 1 you cannot. You need to borrow 1 from here, which also you cannot. You need to borrow 1 from here, and this becomes 1, 0. And you borrow 1 from it, and it becomes 1. So here 1, 0, that is 2, minus 1 is 1. And here 1 minus 0, that is 1. And this is no longer, see, this is 1, 0. You subtract 1 from it, and it is 1. And this is 1, 0, because you need to borrow 0 minus 1. Okay, so you need to borrow. As you can see, borrowing is rather complex. Borrowing is rather complex. This is an example of borrowing. Please study it and take your time with it. However, if we just convert the second one to its 2's complement, if we just convert the second one into its 2's complement, that is 0, 1, 1, 1, 0, 1, 0, 1, starting from the right. When we find the zeros, we copy. We don't have. We copy the first one, and we keep flipping. So this is the 2's complement of that. After that, you may change the subtraction to addition. You may change the subtraction to addition. So it is 1 plus 1, that is 0, and carry 1. Okay? And then it is 1 plus 1 plus 1, it is 0, and carry 1. Okay? Please take your time and do these additions. This is the original question, and this is the 2's complement. Okay? Take some time to work them yourself. Okay? And then, inshallah, you get the same answer. Thank you very much for your patience. These 2 last exercises were really difficult and very recent. Okay, so this is the level of difficulty that you are supposed to deal with. I always like my students to be up to date. Let us move to something easier. Let us move to something. There is something called BCD, binary coded decimal. When it comes in a very easy way. Okay? Because it has a little problem with its mathematics, but we will live with that. The binary coded decimal representation has a small issue in its representation, and we will live with that. And they will keep asking you about incorrect representation. I will show you the questions that appeared in past paper. This is my job. There is something called binary coded decimal, abbreviated BCD. The BCD codes use 4 bits to represent a denary digit. Each denary digit is written as a 4-bit binary number. This sentence is mathematically incorrect. It should have been, to be mathematically correct, it should have been every hexadecimal digit is written as 4-bit binary number. Okay, if you would like to be exact, but BCD is not exact. BCD is treating binary numbers and converting them into denary as if you are converting them into hexadecimal. This is not mathematically correct, but please keep this aside. I will show you the method. I will show you problems with it, and I will tell you exactly how to do the conversion and earn all the marks. Okay? In binary coded decimal BCD, each individual denary digit is written as 4-bit number. This is mathematically incorrect, but we have to live. It should have been every individual hexadecimal digit is written as 4-bit binary number. It should have been, but I will live with that. I will live with that. Okay, shabab? So binary coded decimal, it is very, very, very simple. If you have 46 in denary, you convert the 4, and this is 0, 1, 0, 0. And you convert the 6, it is 0, 1, 1, 0. Because if you put weights 1, 2, 4, 8, this is gonna convert into 4. And here, if you put 1, 2, 4, 8, so it is 4 plus 2, and it converts into 6, and that's it. It is as simple as that. You split a denary number into digits and convert every single digit on its own. This is called binary coded decimal. Okay? Okay, let us do examples. Binary number is split up into groups of 4 bits. Starting from the right, each group of 4 bits is converted into a denary digit. It's so simple. 0, 0, 0, 0, 1, 1 is converted into 3. 0, 1, 1, 1, it is 1 plus 2 plus 4 is converted into 7. It's so simple. Okay, let's carry on. Let's carry on. Write the number 359 in BCD. Convert the 3 on its own. That is 0, 0, 1, 1. Because 1 plus 2 is 3. Convert the 5 on its own. It is 0, 1, 0, 1. 0, 1, that is 4 plus 1, that is 5. Convert the 9 on its own. It is 1, 0, 0, 1. It is so simple. So the 9 is 8 plus 1. This is under the 8 and this is under the 1. See how simple it is? Okay, let's carry on. Convert the binary coded decimal BCD 0, 1, 1, 0, 0, 1, 0, 1 into denary. Okay, this is 1, 2, 4, 8. So it is 4 plus 2, that is 6. Put the weights 1, 2, 4, 8. So it is 1 plus 4, it is 5. Thank you. Okay? Okay? Let us see some examples, because they talk about mistakes in BCD. I told you it is not mathematically exact. It is treating the denary as if it is hexadecimal. This isn't mathematically exact, but we have to live with that. They have reasons. They may ask you, why would you ever use BCD? I will tell you the reasons that showed in the exam. And thank you. This is a cover topic. Let us look at this. The 3-digit BCD representation has been incorrectly copied. It is shown as 0, 1, 0, 0, 1, 1, 1, 0, 0, 0, 1, 0. They ask you to recognize the mistake. Okay, okay. You split them into groups. This is a group, and this will convert into this way 1, 2, 4. This will convert into 4. It's okay. This is another group. I have a problem. This is converting into something that is greater than 9. This is possible when you're talking about hexadecimal, but you are talking about denary, and this is BCD. So the second block, this one, because it is 0, 1, 2, 4, 8. So it is 2 plus 4 plus 8, and this is 14. And you cannot represent 14 in denary. You can only go to 9. This isn't hexadecimal, and this is the cause of mistakes. This isn't hexadecimal. Okay, the second block of 4-digit, that is the one highlighted in red, is a digit larger than 9. It is 14, and you cannot represent 14 in denary. So this is the mistake. That was the question, and that was the answer. Okay, and then we ask you, why would you ever use BCD? BCD is used when denary numbers need to be electronically coded. For example, to operate a display where each digit is represented. You just want to send some digits to the display to display them, and that's it. You cannot apply mathematical rules to them because they aren't correct. Okay? Decimal fractions can be actually represented. Students doing A2, they will see the complexity of representing fractions in binary. So if you have a fraction and you just want to display it and you don't want to go into that complexity of representing a fractional part in binary, because actually not all fraction parts can be exactly represented. Okay, then you use decimal BCD. Decimal fractions can be accurately represented using BCD, just displayed. A string of digits on any electronic device displaying numeric values. So these are the cases where you could use BCD just to display a value on the screen. And then there was another question. These are all the past paper questions that I came across. I just keep loading my notes with past paper questions. Benefits of using binary coded decimal. Straightforward to convert to and from BCD and binary. It is just straightforward. So it is less complex to encode and decode for programmers. Okay, easier for digital equipment. Use BCD to display output, just to display output, some information. Okay, can represent monetary, which means money, values exactly. The BCD is just used for representation. Okay, please let me cover this and carry out this exercise yourself. As you can see, my notes is loaded with examples. The hexadecimal value 11 represented in binary. Please go ahead and convert 11 hexadecimal. So you put the weights 116. So you put the weights 116. I think I'm faster than you. 1 plus 16 is 17. So 1 in hexa is 17 in binary. See? I'm doing it faster than you. The smallest binary number that can be represented by an unsigned. Unsigned means there are no positive, no negative. 8-bit binary integer. I think it's going to be 0. The smallest binary number that can be represented by an unsigned. Unsigned means there are no negatives. So the smallest value will be just a 0. Okay, excellent. The binary number 87 represented in binary coded decimal, BCD. Just convert the 8. The 8 is 1000. And convert the 7. The 7 is 0111. See? This is the 8, 1000, and this is the 7, 0111. It's so simple. BCD is very, very simple. The binary number 240 represented in hexa. Oh, you have now to do long division. Now I have to give you some times. Even me, I cannot do it that fast because I need to binary number 240 divide by 16 and find remainder. The binary number -20 represented in 8 bits 2's complement binary. Go ahead and do the workouts. Work them to yourself. And I show you the answers after a few minutes. Let us do this again. 11 in one. I don't call it 11. It is 11 in hexadecimal. Okay, I can draw. This is 1 in hexadecimal. Let me put weights. Above the 1, I put 1. and here I put 16. Remember old days when you used to convert denary, when you used to convert hexadecimal into denary, you put weights 1, 16, 256. Here you don't have 256. You multiply and add. So 1 multiplied by 1 plus 1 multiplied by 16. So 16 plus 1, and this is 17. So easy. Huh? How do you think? Here you need to do division. Here is another story. You start with the denary 240. You start with denary 240. You have to divide by 16. Without a calculator, calculators are not allowed. Okay, so let me clear this drawing first. So for this, you have 240. Okay, divide by 16. Okay, you have the denary number 240 represented into hexadecimal. Okay, so 24 divide 16. I think 24 goes into 16 once. So this is 1. Let us find the remainder. 1 by 16. And then subtract. And this is 6, isn't it? 24 minus 16. No, this is 8, I guess. 24 minus 16 is 8. And then let us pull down the 0. Okay, 80 divided by 16. Okay, 80 divide 16, you get 5. 5 multiplied by 16 is 80. Subtract, there is no remainder. Okay, so 240 divided by 16 is 15, remainder 0. Okay, so you write here the 15 as F and the 0 as 0. So 240 becomes F0 in hexa. 240 becomes F0 in hexa. So now when you get a number in denary and you like to convert it into hexa, you get a number in denary and you like to convert it into hexa, you divide by 16 and find the remainder. So 240 goes into 16 15 times with a remainder 0. So the 15 goes into here as F. And the remainder goes into here, 0 is 0. So 240 is F0 in hexa. Let us redo this again, because you are asking me. You have 1 1 in hexa. You have 1 1 in hexa. Let me do it here. This is 1 and this is 1. And it is hexadecimal. You put weights. Here 1 and here 16. Multiply and add. 1 multiplied by 1 plus 1 multiplied by 16. So 16 plus 1 is 17. This is one way. This is one way of converting a hexa into denary, is by multiplication. The other one is more difficult. If you want to change denary into hexadecimal, you do dividing. Okay, and all this is just O level. This all hexadecimal and denary and hexadecimal is just O level. Please refer to the O level, because in the O level, they give you plenty of time to exercise. Here, we are in a hurry. They don't give you a lot of time to do that in the AS. I hope everything now is clear. The last one, the last one is also needs consideration. Let me get rid of all this drawing on my screen. Okay, so, okay. So let us check. Here we have F0 as we anticipated or as we calculated. Okay, now the denary number -20 represented as 8-bit 2's complement. Okay, first find the representation of +20 and make them 8 bits. Find the representation of +20 and make them 8 bits. And then get the 2's complement. Okay, I will do that for you. Please notice that exam questions in the 2023 is getting little bit harsh in that. This used to be a complete question. And now it is just one in a table. Okay, the -20. The -20. First, we get the binary equivalent of the magnitude 20. And we put it in 8 bits. Okay, so it's going to be 16 and 4. This is the representation of 20. But we don't want 20. We want -20. We apply the FAST method of finding the 2's complement. Starting from the right, we get the 2's complement by the FAST method, which is moving left. Starting from the right, move left. Copy any zeros. Let me put that in blue. Copy any zeros up to the first one, which is also copied. Yeah, first 0 is here, another 0 is here, until I get the first one and it is here. And then start flipping. And then any remaining bits are changed from 0 to 1 and from 1 to 0. Here, and I'm flipping. And this representation is just the answer. The problem is they are not giving you much time to do this, because now these are in the O level. Negatives are now in the O level syllabus 2023. Okay, so you are supposed to be doing this as a revision. Okay, shabab. So see that table, it took us a lot of time. Please do a lot of practice. This is the new stuff you need to train for. My classified is so full of older questions, but these are the most recent. Okay, train on both. Let us look at this. Convert the unsigned binary integer. This is unsigned, meaning there is no positive, no negative. ماشي? Into binary coded decimal. To convert the unsigned, ماشي, we first find the decimal. This is not that easy. This is not that easy. You have unsigned binary integer. We like to convert it into PCD. It's not that easy. I thought it is. To convert, let us take it. These are all copied from 2023. These are all copied from 2023 exams. And as you can see, they are not a bit new to me. Okay? Because they are just appearing. They are here in my updated notes. Okay? Convert the unsigned. So now you have a challenge. You need to convert. We first find the denary. We first find the denary equivalent. Find the denary equivalent of that. Yeah, go ahead and do it fast. Find the denary equivalent of that. 1, 2, 4, 8, 16, 32, 64, 1, 2, 8. Do them fast and add. Give yourself a chance. They're gonna be 149 denary. Now you need to convert 149 denary into BCD. That is the one on its own, 0001, and the 4 on its own, 0100, and the 9 on its own, 1001. See, that was on 2023 June, or maybe November, Okay, Shabab? So you are given a binary number. How could you convert it into BCD? You go first into denary, and from denary, because BCD is binary coded decimal, you go from this into here. Maybe that's why they are calling it decimal. They are calling it decimal, but we used to call it denary. Okay, Shabab? How can you see tricks of 2024? Okay, and that's another example. That's another example. Let me cover it and ask you to do it yourself. Please go ahead. Please. Hexadecimal 3A. Put the weights 116. And remember that A is 10. BCD. Binary. 2's complement binary. This is going to be something negative. Okay, please go and convert these. I can give you clues. Things in gray are not connected, because actually this is the mark scheme. So please give yourself time and do this exercise. Okay, this is the answer. Let me do the hexadecimal 3A for you. 3 is 3 and A is 10. This is hexadecimal. And to convert it into denary, you need to put weights. Hexadecimal weights. Hexadecimal is base 16. So weights are 16 to the power of 0, 16 to the power of 1, 16 to the power of 2. So weights are 116, 256. Fortunately here, we don't have 256. Let us do it by hand. Let us do it by hand. I have here 3A. This is 3A. And remember that A itself is 10. Okay, put the weights. Weights are 1 and then 16. And you don't need the 256 because they are only 2 digits. Let us multiply by and add. 3 by 16, it is 3 multiplied by 16 plus, this is 10. This is 10 multiplied by 1. So it is plus 10 multiplied by 1. So 3 by 16 is how much? So 3 by 16 is 48. You have to study and memorize the 16 multiplication table, because you will be doing that without a calculator, and you need to do that fast and accurate. So 3 by 16 is 48 plus 10. I think it is 58, and it is that answer. See? Okay? Oh, everything in here is in the O-level syllabus except that. BCD isn't in the O-level syllabus. So you are supposed to do that really fast. And probably they're not going to award you a lot for that. Okay? Okay, that's it. Okay, let us do something else, because it took us a lot of time to do the hexadecimal and binary and denary. Okay? Okay, internal coding of text. Let us discuss this, because you should know this also from the O-level syllabus. We have what is called a character set. because the computer can only store binaries. And to represent alphabet, there is what is called ASCII code. And ASCII code is one of the two character sets you should be familiar with. So the ASCII code is a character set. I will go through everything from the beginning, but just let me explain it the easy and fast way, and then let us read everything. So the ASCII code, this is the table of the ASCII code. You are not supposed to memorize it, but maybe you need to play with it a little bit. Okay? You need to play with it a little bit. Is that, for example, they tell you that the ASCII code for A is 41 in hexa. What do you think is the ASCII code for E? You know that A, B, C, D, E. So 41 comes after it, 42. I don't call it this 41. This isn't 41. This is 41 because this is hexa. So 41 followed by 42, followed 43, 45, 4, 4, 4, 5. Okay. Okay. So yeah, and also all the programming in the O level and in the A, and I'm sorry, in the AS and in the A2 will be using the ASCII code. You are not supposed to memorize this at all, but you have to be very much familiar with it. You have to be very much familiar with it. So for example, this is the ASCII code for A capital, it is 41, and this is the ASCII code for A small, this is 61. Maybe this is the ASCII code for Z, that is 7A. Okay? You count in hexadecimal like that. 41, 42, 43, until 49. After 49, you get 4A. After the 9 is A. And 4B, 4C, 4D, 4E, 4F. And after the 4F, you get 50. Okay, I'm practicing hexadecimal. Okay, so ASCII code used to be 7 bits, and extended ASCII is 8 bits. And there is a little problem with that. Okay, so let us look back at the ASCII code. This is letter A. Letter A is represented into the computer using a binary number. Letter A. Everything in computer is ones and zeros. So letter A and letter B and letter C are encoded using what is called ASCII. What is called ASCII? It stands for American Standard Code for Information Interchange. It is written here. Okay? Okay. So the letter A is represented by a binary number, and that binary number is hexadecimal equivalent. The hexadecimal equivalent of that binary number is 41. So actually all these are represented in binary. The computer can only store and process binary numbers. Okay, so a binary number that is encoded as ASCII, this one will be letter A, letter B, letter C, and that's it. Okay, let us come. What do we have to know about this? What knowledge do we need to know? This is called a character set. Let us go and start and read from the beginning. Internal coding of text. If text is to be stored in a computer, it is necessary to have a coding scheme that provides a unique binary code. Everything is represented in the computer in binary. Everything is represented in the computer in binary. Okay? Unique binary code for each distinct individual component item of that text. Such a code is referred to as a character code or character set. Okay? Okay. This is in general. So a character set, the symbols the computer can recognize or use. It is a list of characters recognized by the computer hardware and software. You need to know the definition of a character set. And you have to know that there are two popular character sets, the ASCII code and the Unicode. I didn't talk yet about the Unicode. Or you can say you have three character sets: the ASCII code, the extended ASCII code, and then the Unicode. Let us compare between them, because this is the knowledge you need to know for the moment until we go into programming and start playing with ASCII code with program. It's going to be very easy, inshallah. Okay? ASCII code is 7 bits. Then it can store 2 to the power of 7 distinct characters, and that's it, 128 characters. And this is the picture of it. This is the standard ASCII. If you count them, they are 128 characters. Because when you only have 7 bits, you can only store 2 to the power of 7. Remember that 2 to the power of n thing. It's going to live with us. Okay? So when you have ASCII, when you have 7 bits, you can only store 2 to the power of 7, and that's 128 characters. Okay? That is the standard ASCII. Standard ASCII was invented only for English, because computers were invented in the US. They didn't think of other languages at that time. And then they thought, okay, let us invent what is called extended ASCII. And it's going to be 8 bits instead of 7 bits. And then it can store up to 256 characters. It may accommodate for some special French symbols and some Italian symbols, or maybe Russian, maybe. And then they have to face that there are more languages in the world, especially Japanese and Chinese. Each language of these may have up to 5,000 characters, distinct characters. And then they said 8 bits isn't enough at all. So they moved to what is called Unicode. Unicode is 16 bits long. And then 2 to the power of 16 is 65,000. Is 65,536 different characters. It may accommodate all written languages in the world. And now this is adopted on the internet. The internet is all operating using Unicode, because you may open a page and it is in Japanese. You cannot go and alter the configuration of your computer to properly display the Japanese. Unicode is doing this automatically. So what do you need to know? You need to know that 8 bits or 7 bits is not sufficient to represent all languages in the world. And then 16 bits is big enough, because 2 to the power of 16 is 65,536 different characters. And it can accommodate all written languages in the same code. However, if they ask you, I will go now and read everything. They may ask you, what is the disadvantage of using Unicode? You may say it takes more memory, because every character is represented by 16 bits rather than 7 or 8 bits in the ASCII or the extended ASCII. Okay? Okay, that's it. That's all what you need to know. Nothing more. The definition of character set, properties of the ASCII, extended ASCII, and Unicode. And let me go through it, because probably there are going to be loads of exam questions and mark schemes in between the lines. Okay? Okay, let us have a look. So we know what now a character set is. By definition, they may ask you, okay, the ASCII code, the scheme which has been used for the longest time is the ASCII. It stands for American Standard Code for Information Interchange. Okay? This is an internationally agreed standard. The ASCII uses 7 bits. It was invented long time ago. The power of 7 is 128 characters. ASCII is used for English only. Then they invented the extended ASCII. They made it 8 bits. And then 2 to the power of 8 is 256 characters. That question was once in an exam. But I think it's a little bit old. And let's go through it fast, because it's really exhausting. The ASCII code for A is 41 in hexa. The ASCII code, what is the ASCII code in hexadecimal for Z? How can you find it? Just go and count A, B, C, D, E, F, G, and just hopefully you don't forget a letter. You don't forget a letter. Just go and write them down. If I'm in an exam, the 41 is the ASCII code for A. So I got A, B, C, D, E, F, G, and I don't miss anything. And then write 41, 42, 43, 4 until I get the Z is 5A. So if you put here 5A, get the mark. That was once in an exam, but long time ago. They don't ask questions like this anymore. Okay? And there is another example for it. You say 41 and you add to it 25. But that addition is really boring. Just use that elementary way of writing them down. And then we may practice more about this in programming, but we will practice that in Dinary, because this question, just go through it and study it. I don't want to waste your time right now. Okay? Disadvantage of ASCII, that once in an exam. That was once in an exam. Only 128 or 256 characters can be represented. Uses values from 6 to 128 or 255 if extended. And this is only 1 byte. Many characters used in other languages cannot be represented. In extended ASCII, the characters in extended ASCII, I don't have a picture here for extended ASCII. I don't care. In extended ASCII, characters from 128 to 256 may be coded differently in different systems. They try to make use of it to accommodate for the Italian and for the French. But then it showed lots of issues. And then they said, let's get rid of all that. Let us do the Unicode. The aim of Unicode is to be able to represent any possible text in coded form. In particular, this includes all languages in the world. But they try to make it a little bit backward compatible. The first 128 characters in the Unicode are the ASCII codes. Unicode is 16 bits, which gives 2 to the power of 16, 65,536 different characters. Unicode has greater range of characters than ASCII and represents most written languages in the world. Okay? Unicode uses 16 or 24 or 32 bits. That was once in an exam. Unicode may use 16-bit, may use 24 bits, may use 32, but I just would like to restrict it to 16 bits. Okay, Unicode is designed to be a superset of ASCII. Unicode is standardized. Now it is adopted by all the world. Unicode is designed so that all characters in other languages can be represented. Okay, the Unicode value for character 1 is Dinary 49. The hexadecimal value for the Unicode 1 is 37. The Dinary value for Unicode character 5 is 53. Yeah, this is, so they give you they give you the Unicode or the ASCII code or whatever for 1, because 1 is also represented here. 1 as an ASCII. Okay, so you just count. So 1 and you go to 5. It's just counting. Okay, but here is denary. Okay, I hope I'm not confusing you. I hope this is clear. I hope this is clear for you.